Hi guys, this is section 2 of chapter 11. So we have been working on the geometry lessons, right? Today we're going to talk about curves, polygons, and symmetry. Sounds really interesting, isn't it? Alright, so in the daily language, we all use the word curve to mean not straight. But in math, it's going to be a little bit different. We include straight line as a curve as well. Okay, so in our class and in other mathematics class, if you draw a path without lifting the pencil, which is continuous, right, and without retracing any part of the path except a single point, it's gonna be curve. Okay, so here is a Khan Academy video. I'm gonna show you a little bit. It's a little bit slow. Okay.
You notice that your hand get a little bit bored, so you start daydreaming, and all of a sudden, you notice that your hand has a life of its own, and you start drawing something on the corner of the textbook somewhere. And maybe you draw something more beautiful than this. But what you've just done here is draw what in maths we call a curve. So, what is a curve? Almost anything you do on a piece of paper, where you start somewhere, you do something, and then you stop, is a curve. So, if I do this, then I've drawn a curve. Almost anything you do. So, then what is not a curve? If I draw a circle, have I drawn a curve? Yes, I have. I've started from a point, gone, and stopped. Now, what you notice here is in all these cases, I didn't have to take my hand off the piece of paper. I could just start and do the whole thing. So, all of these are curves. But if I now add, maybe I don't know, this looks like a face to me. If I add two eyes over here, then what I've done is that I have made this have gaps. So, you can see the gaps here. You cannot go from this part of this picture to this without taking your hands off. So, this gap, let me mark it out over here. This gap is also called a discontinuity. You can just call it a gap. So if there is a gap, then it's not a curve. So if you want it to be a curve, then it has to be what we call continuous. So maybe if I do this, if I take this and if I connect it with some specs, if I do this and then connect it like this, then what I have is a curve. But if I have that gap, then what I have is not a curve. Now what if I draw a straight line? And then if I ask you, is this a curve? What would your answer be? Think about that question. In daily life, we keep saying that a road can either be straight or it can be curved. But in maths, look at what we said. If you start somewhere and go somewhere else and then you stop, as long as you know there are no gaps, what you've drawn is a curve. So then, is a straight line a curve? Yes, it is. Even though in daily usage we don't call it a curve. So you can see that in maths, some of the words have different meanings than what they have in normal language. So if this is a curve, if one line is a curve, then think about this. If I take it, draw one line like that, and then draw another line like this, is this a curve? I'm just marking these corners big. This could have just been drawn like this. So this is a curve, this is a curve. These two are almost same. Maybe I'll do this. Is that a curve? Yes, it is. I started somewhere and there are no gaps between each of these lines that I've drawn. I can even make this bigger. I can draw something like this. Maybe a kite. This is also a curve. So just because we use the word curve, a lot of people think that the lines should be curved like this and cannot be straight lines. In fact, they even say you should not use the ruler. You use whatever you want to, but make sure that the whole thing is connected or continuous. And now that you know what a curve is, maybe we can begin to play with it. If I take you down here and if I ask you, okay, you see some curves over here on the left and some more curves over here on the right. Can you take a minute? Just pause this video now. Take a minute to see, is there a difference between these two? And if so, what is that difference? Now, if you thought about it, you may have noticed that in all these curves on this side, you never see what we can call a crossing. So to draw this curve, in some sense, you have to go like this, go all the way here and then cross yourself at this point. But you don't see that happening anywhere over here. Over here again, you can see that there is a crossing. And then here, where is the crossing over here? It's right over here. here it's over here. Now, on this side, no matter where you draw whatever you're drawing, you can just draw it completely. You'll notice that all the curves that do this, in other words, they don't cross, are called simple curves. S-I-M-P-L-E, simple curves. They don't cross themselves. And those curves that do cross themselves are called, at least I'm going to call them not simple curves. Not simple. Maybe there's a more serious sounding name for this, but I guess this should do. Now, what's these two last diagrams over here? If you look at them, to draw them, I actually don't have to cross, right? I can just go like this, go here and come here. So we've used the word crossing, but there is a better way to say the same thing. So what is it about these not simple curves that you should know? The idea is that anytime you pick a point over here, maybe I pick somewhere here, maybe I pick this point. If you look inside, you can see that there are only two lines leaving from this point. If I pick, say, this point, I can see there are two lines leaving from that point. So anytime that I pick anything that I want, even in between, I can just pick a point over here and say there are only two lines going over here. In fact, you might have even asked, isn't this crossing itself in some sense? Because I start somewhere here, go all the way, and then I have to come back to the same point, right? That happens in all these cases. Whenever you do that, even if you do that, it's still a simple curve. But if you can ever draw, say, a circle and find that inside this, if you take a point, there will be three or more lines coming from there, then it's not simple, right? So I hope you can see that difference. Over here, if you draw that circle, if you take this point, how many can you find? 1, 2, 3, 4. 1, 2, 3, 4. Even if it's not 4, even if it's just 3, that's enough. So over here, you can see that there is 3. That's enough to make the curve not simple. When I was in school, I remember that I used to have one favorite curve that I used to keep drawing on my textbooks and get scolded. So my curve was this. I used to love drawing what I think it's called a spiral, and it was always very fun, a lot of fun to draw, especially because I used to find it hard to keep this gap between the two lines the same. And the reason I used to love drawing this is because once I finished drawing it, then I could look at it and it looked like it's rotating. I don't know why that happens, but it used to look like it's rotating even though it's not. Oh, it became ugly over here. Now the question for you is, what I've done here, have I drawn a curve? Is this a curve? In other words, are there gaps in this or not? Also, is this a simple curve or a not simple curve? Not simple curve. Think about that question.
So what do you think? Yeah, it should be a simple curve because there's no crossing parts, right? Okay, so you have learned about simple curve and non-simple curve. So we know about this now. A simple curve is a curve that does not intersect itself. So take a look at this. It is a simple curve because whichever part you pick, there are two lines on the other side, on both sides, right? Okay, so there's no crossing, so it is a simple curve. It is also simple curve, right? Just like the spiral he made, because whichever part you pick, there's only two lines going both directions. How about this one? It's not a simple curve because, as you can see, here's a crossing part, right? And you have 4 lines that goes from this point. So it is non-simple curve. Now, what is a closed curve? When the curve is closed. So when you start from one point and you end at the same point, then it is gonna be the closed curve. So like this, closed curve. This is also closed curve. Okay. So what is a polygon? 2 words that you have to remember is straight lines and closed curves. Okay, straight and closed. I highlighted them here. So polygons supposed to be straight lines, not just any curve, but it has to be straight curve, and also has to be closed. So let's look at the first example. Is this a polygon? So let's see. Are the sides, all of these 5 sides are straight? Yes. Is this a closed curve? Yes. So it is a polygon. How about this one? It is all closed but it's not straight line here, so it's not a polygon. How about this one? Has all straight lines, but it's not closed, so it's not a polygon. Okay, in polygon we have to know some terminologies here again. So vertex or vertices for plural. Each vertex is a point where two or more line segments meet. So like this line and that line meets there. So it's a vertex. For 3-dimensional 2, you have 3 lines meet there. So it's gonna be a vertex. Okay. For a polygon, an edge, these are the edges. Okay. The edge is a line segment on the boundary joining on the vertex. So edge is connecting both endpoints. So it's very similar to the line segment, isn't it? I prefer to use edge than side, because when you think about 3-dimensional, if we say this is side, it's very similar to the side here too. Excuse me. We call that base, but it's kind of confusing, so I think edge is a little bit more specific and not confusing. Okay. In polygon, there are 2 types. One is concave and another is convex. The difference is concave, like cave in, it goes in. So if you compare these two, you can see this angle goes inward, right? So this polygon, if you see interior angle here, it's greater than 180 degree. Straight line is 180, but it's bigger than that, then it becomes a concave. Okay, just one is good, usually just one, but if you find any internal angle is greater than 180 degrees, then we call that concave. Otherwise it's convex. So like regular polygons, like equilateral triangle, square, equilateral, octagon, heptagon, whatever we have that convex, right? So convex polygon has no angles pointing inwards like that, right? No internal angle is more than 180 degrees. So let's take a look at this. Straight line comes here, is less than 180. Same here, less than 180, less than 180, less than 180, less than 180. Then it is convex. Regular or irregular. Regular polygons have all angles equal and all sides, all edges are also congruent. Otherwise, it's called irregular. Okay, so you need to have the same length on all edges, all sides, and your angle has to be all equal. So equiangular and equilateral. Equilateral means equal length. So let's take a look at some other things here. Simple or complex. So simple polygon has only one boundary and it does not cross over itself like this one. It's simple, but like this one, it is a polygon, but it's a crossing over itself. We call that a complex polygon. Okay, so let's take a look at this. What do you think about this? Is this concave or convex? So think about concave or convex for all of that, and think about if it is simple or not simple. Okay, so, and regular or irregular. Why do we say it's irregular? Because the length here are not all congruent. This is much longer than these two, right? So when you have different length, it is irregular, because regular has to have same length, also same angles, but looks like the angles are not congruent. This angle is much bigger than this one, so we call that irregular. Hexagon, because there are 6 sides. This one has 8 sides, so we call that octagon. It is a polygon, but it's not irregular, and also it's a concave, because you can see this angle here is bigger than 180, right? And it's a simple, and this is also simple. Is this concave or convex? This is convex because no angle, interior angle is greater than 180. How about this one? This looks like a regular because all sides are congruent and all angles are congruent. However, it's a complex polygon because a star polygon here, we can see a lot of crossing lines there. So it is complex, not simple. Okay, let's look at interactive polygons. I think this is cool for you to teach for your middle school students, even 6th, 5th grade students. So it shows a regular pentagon. Pentagon means 5 sides. So you have 5 edges, 5 sides. They're all congruent. The lengths are equal and the angles are congruent. So the we call that equiangular and equilateral when the lengths are equal. If I change that somewhat different, it's not regular anymore. It becomes irregular. This is still convex, but if I change it, it becomes concave because this angle is greater than 180. But it's still pentagon because I still have 5 sides. Okay? Alright, so this is something cool thing that you can do with your students. And let's take a look at the polygons and its names. So we already know like triangle, quadrilateral, pentagon, hexagon. So these names are coming from Greek, I guess. So tri means 3, so 3 angles. So you have 3 angles. 3 angles means you have 3 vertices, also you have 3 sides. Quad means 4, so quadrilateral, 4 length, 4 sides, or 4 vertices. Pentagon, penta means 5, gon means angle, so 5 angles, 5 vertices, 5 sides. Hexagon, 6. Heptagon, 7 sides. Octa, like octopus, 8 sides. Octopus has 8 legs. Nona means 9. Deca, 10. And deca, I put the asterisk because we don't use this much. Okay, I just want you to remember the other ones all the way to dodecagon, 12, dodecagon. Okay, and then you can just go 13 gon, 14 gon, 15 gon, ... Okay, so it's gonna be a little bit more simpler if you have more than 12 vertices. Okay, so try to remember these names. Okay, when referring to polygons, you need to list the consecutive vertices in order. So for example, we call this quadrilateral ABCD or ADCB. You're not gonna name this as ACDB. You need to go in order, in one direction, counterclockwise or clockwise. You don't have to start from A, you can start from D, but still you need to go one direction. If you choose to go this way, you can name this quadrilateral as quadrilateral DABC or DCBA, or that same quadrilateral as CBAD or CDAB in order, okay? But you cannot go quadrilateral ACDB like that, okay? What is interior angle? The angle that is inside of the shape. What is exterior angle? We talked about exterior angle before, right? So if you have interior angle, exterior angle is the counterpart of that interior angle on straight angle. So they are supplementary to each other. When you add them together, you're gonna get 180. Remember supplementary and complementary? Complementary angle is when you add those two angles together and the sum is 90. Supplementary, when you add those two angles and the sum is 180. Diagonal, what is diagonal? When you connect a vertex with the other vertex that is not consecutive. Okay, so a segment joining two non-consecutive vertices, which means consecutive means it's right next to it. So you don't connect that, it's not diagonal, right? Because it's a side, but skip that. But next one and next one like that, from one vertex, you can go to non-consecutive vertex, connect that. That segment is called diagonal. So for this quadrilateral, you can draw two diagonal from one vertex. Same from here, two from there. From here you can draw 2, from here you can draw 2, from here you can draw 2, but the sum is not 2 times 4 because some of them we counted twice. Okay, so we will talk about the number of diagonals for polygons we listen to. Okay, so sometimes I talked about congruent. What does a congruent mean? Even if you turn, flip, or slide, the shape, the size doesn't change, then it's called congruent. So it's exactly the same size, whether it is a length or an angle. Okay, so angles can be congruent when they are the same measure, same size of the angle in degrees or radians. Size, edges can be congruent when the length are congruent. We usually use, bar like that, saying that, oh, this and that have same length. And the notation for that is this, congruent. So side AB, segment AB, and segment CD are congruent. But here, I didn't put congruent sign, but I put equal sign. Why? Because without that notation, that means it's the distance between A and B. The length is equal, right? Because it can be twinge. Twinges and twinges are not congruent. They're equal. So we put equal sign. So be careful. Similar here. This is the name of the angle. Angle XYZ. Angle XYZ and angle RQP, we're talking about the shape, so they are congruent. But measure of angle, this measure of angle is about the numbers, so they are equal. Does it make sense? Again, when you have this notation like segment, we're talking about the shape. So shapes are congruent. Okay, shapes are congruent, but the size, the length has to be equal. Same here. Okay, so remember to use correct notation. Now let's go to regular polygons. We already have talked about regular polygons. To be regular polygons, the polygon has to have equiangular and equilateral. Equiangular means equal, angular, angle. Equal, lateral. Equilateral means same length. So regular polygons have same length and it's and not or, same length. Okay, so let's take a look at this example. It is a polygon 1, 2, 3, 4, 5. So what is it? Pentagon? It's a pentagon, but it is not a regular polygon. It's irregular. Oops, 1, 2, 3, 4, 5. Oh, this is not hexagon, isn't it? Did I count it wrong? It's pentagon, because 1, 2, 3, 4, 5. Yeah, there are 5. I need to correct this. Okay, anyways, it's not a regular polygon, it's an irregular polygon because the lengths are not equal and also the angles are not equal. So not equiangular, not equilateral, which means it's not a regular polygon. How about this one? As you can see, all of these angles of this hexagon is 120 degrees. So it's equiangular, but is it equilateral as well? As you can see, this is longer than these, right? So it is not equilateral, just equiangular. So it cannot be a regular polygon. It's irregular. How about this one? It says the sides, all of these 6 sides are congruent. So it is equilateral, but it's not equiangular because this angle is so much smaller than this angle. Okay, the angles are not congruent. So it is not a regular polygon. So regular hexagon has to look like this. All sides are congruent and all angles are congruent. So it is equilateral and equiangular, okay, to be a regular polygon. Okay, so in regular polygon, we can find interior angles there. So I am extending the table that we learned from the names of the polygons, right? So we already know and we already know the shape. This shape is just regular polygon. Remember that. These two are about regular polygon. And we know the interior angle is a 60-degree angle for regular triangle. because we know the sum of triangle is 180. If the sum is 180, each one has to be 180 divided by 3 because there are 3 angles, right? Similar to here, we can find, each of these angles. We will talk about that too, how to find it. Okay, so let's talk about triangle first. The figure formed by 3 segments joining 3 non-collinear points. Why non-collinear points? If you have collinear points, all 3 points are on a line, you cannot form a triangle, right? And each 3 points is a vertex. And the plural is, of course, the vertices. Segments are the sides of the triangle or edges of the triangle. Okay, so triangles can be classified by the number of congruent sides. So this is the first classification using the sides, okay, the edges. And we're going to classify differently using the angles too. So if we classify triangle by the number of congruent sides, we know there are no congruent sides. We call that scalene triangle. Remember that? Okay, no sides are congruent. They are all different length. Isosceles triangle, you have at least two sides are congruent. Equilateral triangle, all sides are congruent. So isosceles triangle include equilateral triangle. Equilateral triangle is also isosceles triangle because at least two sides are congruent. At least two sides are congruent. Okay, so you can see the hierarchy there. Triangles can be also classified by angle. Okay, so when you have acute triangle, this is acute triangle because each of these angle is less than 90-degree angle. If one angle is greater than 90 angle, we call that obtuse triangle. If you have more than one angle greater than 90 degree, you cannot even form a triangle. Try to make that triangle with two obtuse angles. You cannot make a triangle because they have to be open. So try that. Okay, if there's one 90-degree angle, we call that right triangle. And also, when you have all 3 angles congruent, we call that equiangular triangle. So it makes sense, right? Okay, quadrilaterals. Quad means 4, lateral means sides. So quadrilateral means when you have 4 sides polygon, we call that quadrilateral. What's the properties? What are the properties of a quadrilateral? Yeah, of course, you need to have 4 sides, 4 edges, or 4 vertices, and interior angles that add up to 360 degrees, no matter what shape of quadrilateral you have. The sum of interior angles have to be 360 degrees. So, quadrilaterals have a lot of different shapes. The first thing we're going to talk about is rectangle. So, rectangle is rect plus angle. Rect means right plus angle, right angles, which means all 4 angles are right angles, 90-degree angles. Okay, so when you're looking at this square is also rectangle because it has all 4 angles, 90-degree angle. Okay, so square, not only the 4 angles are congruent as 90-degree angle, it also has to be equilateral. So all 4 sides are also congruent. Then we call that square. And here's a hierarchy. All squares are rectangle because all squares have 90-degree angle, but not all rectangles are squares because some of the rectangles like this, the sides are not congruent, right? Okay, what else do I have to talk about? Oh, there are some properties for the square. The opposite sides are parallel. So these 2 are parallel and these 2 are parallel. So square is also parallel. Hey, how about the rectangle? These 2 are parallel and these 2 are parallel, so it is also parallel. Okay. Okay, and I have mentioned about the square as equilateral and equiangular because it's equiangular, or 4 angles are 90 degree, which means it's a rectangle. And I also said square has to be equilateral, which means all four sides are also congruent. When all four sides are congruent, no matter what the angle is, we call that a rhombus. A rhombus, okay? A rhombus. So, square has the characteristics of rectangle and a rhombus. Okay, so you can already see some hierarchy again here. So square is a part of a rhombus. Not all rhombus is square, but all square is a rhombus, right? Okay. So a rhombus is four-sided shape, again, quadrilateral, with equal lengths. It doesn't matter whether the angles are congruent or not, but all four sides have to be equal. So we can tell square is a rhombus. All square is a rhombus. Okay? Parallelogram. Parallelogram has opposite sides that are parallel. So opposite pair. This pair is parallel and this pair is parallel. Okay? Trapezoid. Trapezoid has at least a pair of opposite sides that are parallel. So if you have only one pair that are opposite, that they are parallel, then we call that trapezoid. So another hierarchy, we get to know all parallelogram is trapezoid, but not all trapezoid is parallelogram. Okay. How about this one? I see that these two, let's talk about this. An isosceles trapezoid has left and right sides equal length that join the base at equal angle. So isosceles trapezoid, I need to talk about it here. So isosceles trapezoid is when you have these two angles congruent and these two angles are congruent. And these two length of the sides are congruent but not necessarily parallel. Okay, then we call that isosceles trapezoid. Okay, kite. Kite has two pairs of sides. I'm going a little bit fast, so I strongly recommend you to re-watch this video to understand more clearly and solve more problems even outside of the homework. Okay, so watch for some Khan Academy videos, or there are a whole bunch of resources that you can have access to, so I strongly encourage you to look at them. Okay, kite has two pairs of sides, but it's different from trapezoid because each pair is made of two equal length sides that join up. So like this, they are not opposite to each other, but they are joining, so they are adjacent to each other. That pair are congruent, and the other pair is congruent, that are joining to each other. They are consecutive to each other. We call this as the kite. You see the difference between trapezoid and kite? So like this, the opposite sides are congruent, right? I mean, not this one, but trapezoid. Actually, I want to talk about the parallelogram. So parallelogram has two opposite sides are parallel, and the length are also equal. But for kite, adjacent ones are congruent, the length are congruent, adjacent pairs are congruent, but the opposite doesn't have to be. Okay, this is also kite because, as you can see, this side and that side are congruent, they are joining each other, and this side and that side, so these two pairs are congruent, so we call that as kite. Okay, so here is the summary of a quadrilateral. Quadrilateral is very important, even if it's a little bit confusing, right? So let's take a look at this again. Square, all sides are equal and all angles are equal as 90 degrees. Rectangle, all angles are equal as 90 degree angle. Okay, parallelogram, two pairs of opposite sides are equal and parallel. So this pair and that blue pair are congruent and they are parallel. Then because of that characteristics, you can get to know these two are congruent, these two angles are also congruent. Okay, but they are not necessarily 90 degree angle. Oops. Okay, trapezoid. In US, we write it this way. In UK, they write it this way. Okay, so trapezoid, at least two sides that are opposite to each other is parallel. Okay, rhombus, angles doesn't matter, they can be congruent, they don't have to be congruent, but all four sides are equal. Okay, and then because of that, opposite sides are parallel. So all rhombuses are also parallelogram. Okay, kite, adjacent pairs, not opposite, adjacent pairs of sides are congruent. Okay, it could be nice if you write this down on your notebook and refer that. Okay, here's a hierarchy. So in polygon, well, of course, there are a lot more than triangle and quadrilateral. I didn't write all of them, but we can, so far we talked about triangle and quadrilateral. Triangle, 3 sides, quadrilateral, 4 sides. So let's look at triangle first. Triangle can be classified as using their equal size, right? So if all 3 sides are different, we call that scalene triangle. If at least two sides are congruent, we call that isosceles triangle. If all sides are congruent, we call that equilateral triangle. In quadrilateral, you can say it's either kite or trapezoid. So what is a kite? Kite, when you have adjacent sides are congruent. Two pairs of adjacent sides are congruent. It is a kite. If you have at least one pair are parallel, we call that trapezoid. Right? In trapezoid, we have two things. If you have two non-parallel sides that are congruent, we call that isosceles trapezoid. Similar to isosceles triangle, you can have two opposite sides that can be congruent but doesn't have to be parallel. Okay, for parallel, both opposite pairs are parallel and equal, and the other opposite pair is parallel and congruent. In parallelogram, we have rhombus and rectangle. Rhombus, all 4 sides are congruent. It doesn't matter with the angle, but all 4 sides are congruent. Okay, if you have all 4 angles congruent, we call that a rectangle. If you have both of the characteristics of rhombus and rectangle, which means all 4 sides are congruent and all 4 angles are congruent, we call that a square. It's very complicated, so you need to practice more. Here is one example from the homework, and it can be in the test, it can be in the quiz, so I strongly encourage you to remember this. So let's look at this example. Isosceles triangle. You can have more than one answer for each of these, okay? Isosceles triangle. So let's take a look at the triangles. A and G are the only triangles. So let's look at A. Is this isosceles triangle? Yes, it is, because it's an equilateral triangle. At least two sides are congruent, right? And how about this one? It is isosceles triangle because these two sides are congruent. Oops. So it is more typical isosceles triangle, but also equilateral triangle. These are also isosceles triangle. How about this? Isosceles but not equilateral triangle. Yes, this one, right? Because this is equilateral triangle. Equilateral but not isosceles triangle. There's none such that equilateral but not isosceles triangle. How about parallelogram but not a trapezoid? The definition of a parallelogram is two opposite pairs are parallel and they are congruent. How about trapezoid? At least one opposite pair is a parallel, right? So we know that all parallelograms are trapezoid. All parallelograms are trapezoid. So you cannot have any parallelogram that is not a trapezoid. So there's none of that. E, a trapezoid but not a parallelogram. This is possible, right? So you can have only one pair that are parallel, then it becomes just trapezoid, not a parallelogram. So let's find that. This is parallelogram. It's a trapezoid, but it is also parallelogram. So not that one. How about this one? They are not, these two opposite pairs are not parallel, so it cannot be trapezoid. You need to have at least one pair that are opposite and parallel. How about this one? Both opposite pairs are parallel, so it's not a trapezoid. This is a kite, just like this one, right? This adjacent ones are congruent, not parallel. How about this one? We see AD and BC are parallel, but these two are not parallel. So only one pair is parallel, then it is trapezoid, but not parallelogram. So we know this one, F. F is parallelogram, but not a trapezoid, right? Okay, anything else? How about this one? We see that these two are parallel and these two are parallel. That's what it says here. That's parallel notation. And this, nothing is parallel, so we see that. How about square? It is a parallelogram because these two are parallel and these two are parallel. Okay, so only F for E. How about F? A rectangle, but not a square. So to be a square, you need to have a rectangle and a rhombus characteristic. So all four angles and all four sides are congruent, but you need to have only a rectangle, so you need to have all four angles that are 90-degree angles, but you are not supposed to have congruent sides, so it doesn't become a square. Okay, so a rectangle, so 90-degree or 90-degree angles, but not congruent size. Which one is that? It's not even 90 degrees, so no. Not even 90-degree angle, no. This is 90-degree angle. All four angles are 90-degree angle, and all four sides are not congruent, so D is good one, right? It's all four sides, but not a rectangle, not a rectangle, not a rectangle, not a rectangle. It is a rectangle, but it's also square, so just D for F. Make sense? How about, come on, G? A square, but not a rectangle. Hey, can a square not be a rectangle? We know that all rectangle is a square, so there is no such thing, right? How about H? A square, but not a trapezoid. What do you think? Same thing. You can, well, all squares are trapezoid because the definition of a trapezoid is at least one pair that are opposite sides, they are congruent. I mean, they are parallel, right? So in square, the opposite sides are always parallel. So there is no square that is not a trapezoid. There is no square that is not parallelogram. There is no square that is not a rectangle. Okay? How about a rhombus, but not a kite? So we know that rhombus means all four sides are congruent. So you're going to find all four sides are congruent. But it says not a kite. To be a kite, you need to have two adjacent pairs are congruent like this. So this is a kite and it's not the answer. How about this one? It is a rhombus because all four sides are congruent. But let's see. The adjacent sides are congruent? Yes, it is. So no, we can't. How about this one? Is this a rhombus? It's not even a rhombus because all four sides are not congruent. How about this one? All four sides are congruent? No. So it's not a rhombus. How about this? All four sides are congruent? No. How about this one? All four sides are congruent? No. How about this one? No. Yes, this is all four sides are congruent, but it is a kite. Is it a kite or not a kite? This is also a kite, right? Because to be a kite, you need to have two of these sides, adjacent sides are congruent. So we also know that square, all square is a kite. Okay, so there is no such thing. Okay, a rhombus. What does that mean? A rhombus, you need to have all four sides that are congruent. All four sides that are congruent, like this. Not all four sides are congruent. No, 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 but this, right? all four sides are congruent. So these blue marks says all four sides are congruent. All four sides are congruent. Okay, how about a kite? What does a kite mean? You need to have two adjacent sides that are congruent. So yes, this is a kite because two adjacent sides are congruent. Two adjacent sides are congruent. Two adjacent sides are congruent. Okay. How about this one? Two adjacent sides are congruent? Yes. How about this one? Two adjacent? Not this one. How about this one? Two adjacent sides are congruent. Yes. Not this one. How about this one? No, because two adjacent sides are not congruent. How about this? Only one adjacent side is congruent, not the other. So no. How about this? Two adjacent sides are congruent. So yes. So for kite, we have 4 answer. B. 4 adjacent. Kite. This is a kite. B, C, E, and J. Right? Okay. If I went too fast, please rewind it and watch it again. Okay. Oh, I also have answers here. All right. Diagonals. Let's take a look at the diagonals. How do you find the diagonals? We already know the diagonals, definition of diagonals. So from one vertex, not the adjacent one, but there's no other, so you cannot connect it to anywhere, so there is no diagonal for triangle, right? For quadrilateral, I can draw 2 diagonals. From pentagon, I can draw all of these diagonals. So from one vertex, not the adjacent one, not the consecutive vertex, but the other vertices, you can draw the line segment. We call that diagonal. So as the number of sides increase, you can see the number of diagonals also increase, right? My question for you is, how can we determine the number of diagonals? So I want you to draw these shapes on your paper and find out how many diagonals you find. Okay, so we know a pentagon has only 2 diagonals that intersect at a given vertex. So if I draw a pentagon, it looks like 5 sides. It doesn't have to be regular, it can be irregular. It doesn't matter, still you have the same number of diagonals, right? So from one vertex, we know that, oh, there are 2 goes here. And from this vertex, also 2. From this vertex, also 2. So we have drawn all the diagonals that I need. So from each vertex, I know I can have 2, right? For pentagon, I know from each vertex, I can draw 2 diagonals. Oh, that means I can have 10 diagonals, right? But if you count them, we have only 1, 2, 3, 4, 5. Hey, that's not 10 diagonals. Why? So I want you to consider that. Why we don't have 10 diagonals, even if we know that from each vertex we have 2 diagonals? Because take a look at this specific diagonal. This is drawn from this vertex, but also it's drawn from this vertex as well. So we actually counted this twice, right? So whatever number of diagonals you can draw from the vertex, we can divide it by 2, right? But also you can think about then how many diagonals can we draw from each vertex? Think about it. From this vertex, we cannot draw a diagonal to the next one. We cannot draw a diagonal to itself. We cannot draw a diagonal to this side adjacent vertex. So we cannot draw 1, 2, 3 points that so these 3 points, these 3 vertices cannot be connected with a diagonal to this vertex. So we have to take away 3 from number of vertices. From number of vertices. And that's how many we can draw from each vertex. But how many are there? There are n many vertices. But since we counted twice for each, from this side direction and the other direction, we need to divide it by 2. So that becomes a formula. So when you're thinking about, let's see, square, for example, we know we can draw only 2 diagonals. From each vertex, we can have 1. From this vertex, 1, this vertex, 1, this vertex, 1. So we know that from each vertex, there's 1. So there are 4 of them. How did we get 1? This is number of diagonal we can draw from the number of vertices. There are 4 of them, but you cannot draw a diagonal to the next one itself and next one on this side. Only 1 is available to draw a diagonal from one vertex. So we got this 1 number from subtracting 3 from number of vertices. And there are 4 vertices, so multiply that by 4. But because we drew this diagonal from this side and also this side, you need to divide this by 2. Then look, 2 and 4, it can be divisible by 2 and you get 2. So there's a total number of diagonal only 2. So it works for any pentagon. Okay, so here's a generalization. Diagonals in polygon. The number of diagonal, write this down. The number of diagonals with n sides or n vertices. The same thing. And number of vertices polygon is n times n minus 3 divided by 2. Okay, remember that. We can easily find the number of diagonals here. So triangle, n is 3 because there are 3 vertices. So 3 times 3 minus 3 divided by 2. We know 3 minus 3 is 0. 0 times 3 is 0. 0 divided by 2 is 0. So there is no diagonal. So you can check with the triangle, there's no diagonal, right? So no diagonal. Decagon, what is decagon? How many vertices are there? 10 of them. So we know 10 times 10 minus 3 over 2, which is 10 times 10 minus 3 is 7 divided by 2. You can simplify from here by dividing both by 2 and you got 5. 5 times 7 is 35. We don't want to draw decagon with the 10 vertices and try out 35 diagonals, right? So it's so much easier if you use the generalized formula. How about 25gon? There are 25 vertices times 25 minus 3 that are not available to draw diagonal. But since we drew diagonals twice from each vertices, both ends, endpoints, so we can divide it by 2. So we have 25 times 25 minus 3, 22 divided by 2. 22 is divisible by 2. So you have 11. 25 times 11, whatever the number is. Let's see actually with my calculator. What's 25 times 11? 25 times 11 is 275. Yeah, number like this, you don't want to count all of the numbers, right? Okay, so n-gon has n times n minus 3 divided by 2 many diagonals. Okay, how about this problem? Determine how many diagonals each of the following has. Pentagon. Same problem. So pentagon has 5 vertices. We know it's going to be 5 times 5 minus 3 over 2. We already did that, right? So 5 times 2 over 2. You can multiply and divide it by 2, or you can simplify from here. I prefer to have a simplifying before you multiply that out. Okay, but no matter what you do in this calculation, you need to have a whole number. You're not gonna have any decimal number there. Okay, if you get a decimal number, that is wrong because you need to get the number of diagonals. You cannot have 2.5 many diagonals. Okay, 18 gone. 18 times 18 minus 3 divided by 2. This is 9. 18 minus 3 is 15. So 9 times 15 is times 9, 135 many diagonals. 19 gone. 19 times 19 minus 3 divided by 2. This is always, I mean, odd number minus 3 is always even number, so it can be divided by 2. So 19 times 19 minus 3 is 16 over 2. Both are divisible by 2. So 19 times 8 is 152 many diagonals. Okay, hopefully that makes sense to you.